And there we go. So recording, this is our official start of the big data class. Welcome everybody. And so these recordings will be posted on YouTube. I'll send out a link to everybody about where that's going to be after class today. And usually it'll take me, I don't know. So I have another class today right after this one, and then there's office hours. So it'll probably take me till the end of the day before it actually gets posted online. Okay, where is the screen sharing button? There we go. So welcome everybody who's just joined us to our big data class. And we'll start today by going over our course webpage. So we'll be using GitHub to manage everything in this course. I sent you out the link to the course webpage over email. And the way this is structured is up at the top, there'll be a folder for every week in the class where we'll have the notes for that week and different assignments going in there as well. And then our syllabus is this main big README file right here. So there's, I'll try on all of our pages to have some sort of fun comic about whatever it is that we're talking about for the week. And so this first one is Dilbert, lots of good Dilbert comics about big data and other programming topics. And the punchline of this one is the pointy-haired boss right here saying, let us pay to all the big data people. So I like to start off all the classes that I teach by what can you make? What can you do with this material? How much money can you make after graduating? And there's this famous website, levels.fyi, where similar to Glassdoor, but really specialized to these computer science, data science kind of topics. And in this class, we'll talk about a lot of this throughout the semester, but there's two new job titles that are in this levels.fyi that you maybe haven't heard of before, but we'll talk a lot about what they do in this class, and that's DevOps and Distributed Systems Engineers. So if you click on the levels.fyi, it takes you to this web page right here. And you can compare salaries for different companies and whatnot. And L3 is the entry-level salary or entry-level position at Google. L1 and L2 are for things like interns and people who are not software, working on software stuff. And so an entry-level salary at Google is in the 180,000 sort of ballpark range. L3 people would typically be working at Google for, say, anywhere from 1 to 5 to 10 years. And so this salary right here is not, it would be, that's averaged over all of those. So not all new graduates, but still all people early stages of their career. These DevOps positions, so what a DevOps person is somebody who's like actually managing the systems that run in the background at Google, not necessarily developing web pages or developing new technologies, but making sure that they keep running. You can see very high salaries here with DevOps as well. And then this distributed systems, really high salaries. And a lot of the things that we'll be talking about in this big data course are really related to distributed systems. And when you have your data, spreading it out over hundreds or thousands of machines so that they all work together efficiently. Yeah, so I'll let you all look at that more as you'd like to. So a little bit more about me. My name is Mike Isbicki. Please just call me Mike. There's no need for Professor Isbicki or Professor Mike. In computer science in general, we're all very informal people, and nobody's going around calling Mark Zuckerberg Mr. Zuckerberg at Facebook, except the lawyers. All the computer engineers are calling him Mark. So you can feel free to just call me Mike. Yeah, I mentioned that, so after this class, I have another class and general office hours after that other class, so 2 to 3 p.m. There'll also be in office hours that is specific just to this class. And I've put out a link to a survey about what times would be good for you all to do that at. And I'll show you the link to that in a little bit when I talk about the this GitHub issues system, which is what we'll be using to do a lot of our communication and collaboration in class here. So some quick fun facts. I grew up in San Clemente, so it's pretty close to Claremont, about an hour away here in Southern California. Spent 7 years in the Navy, did my PhD and postdoc over at UC Riverside, also pretty close to Claremont here. Basically, after going in the Navy, I wanted to come back home and stay in Southern California forever. With the exception, though, that I spent 2 years teaching in North Korea, teaching computer science in North Korea in an academic exchange program. The idea being to improve relations between the US and North Korea by having ordinary people interact with each other and talk to each other. And then the last thing, which will be end up probably relevant to this class a little bit, is my wife is going to have a baby mid-semester. And so depending on exactly when the baby comes, I might have to reschedule a class or something based on that. Okay, so that's about me. Now let's talk about the course, which is probably more interesting to all of you. And so this picture right here, let me zoom in, make it a little bit bigger, is the sort of my map of computer science at CMC. And this is, yeah, so I know a lot of you, about a third of you are from Harvey-Mudd, and then a third from Pomona or Pitzer, and then a third from CMC. And yeah, so this course is part of the data science major at CMC, and it's really designed to be like the sort of capstone computer science course, the culmination of all computer science for data science majors. And because of that, it's really designed for data science majors. And I know many of you are computer science majors, and I'm very happy to have you in this course. But the way computer science works for data science majors is just a little bit different than the way it works for computer science majors. And so I want to spend a little bit of time today talking about what those differences are, so that we're all very clear about what you should expect from this course, and you can be clear for yourself about whether it's the right course for you to take. So at CMC, we have 3 sort of main computer science courses that the data science majors are taking. CS40 is the equivalent of CS5, or I forget the number at, so CS5 is MUD, I forget the Pomona number, but basic intro programming. And the way I think of it is that you're working just on your own computer. And then CS46, our data structures course, the real idea of that course is you're not just working on your own laptop anymore, but you're working on remote servers and getting a remote server to sort of do your bidding and yeah, make it do cool things. And then this course, CS143, the big data course, the way it fits into that is now you're not just working on a single remote server, but you're controlling a big cluster of remote servers, potentially hundreds or thousands of these servers, and getting all of these to work together to accomplish whatever task it is that you want accomplished. And one of the big differences between the data structures course and this big data course is that we really care about scaling to large sets of servers. So making it not just one remote server that you're working on, but hundreds, thousands, possibly millions. And we'll be using programming techniques that it really doesn't matter how many remote servers you have. It's the code that you write, the things that we do will work well on all of these remote servers. And the only thing that is limiting the scalability is how much money you're willing to spend. So if you open up your credit card, which you certainly don't have to in this course, we have all the computing provided for you. But if you wanted to open up your credit card and launch millions of servers on AWS or Microsoft Azure or whatever cloud service you wanted, all of these techniques would scale beautifully to that sort of size of systems. Okay, so that's sort of like quick map of all of CS, and now we'll talk about like what is big data in particular. And this is the sort of thing where it really, really depends on the person who's talking. So most non-computer scientists, who I'm going to start calling muggles because they don't know what they're missing out on. They don't know about all the wizarding world that we're a part of and the cool things that we can do. So they are muggles. Think that anything bigger than 1 gigabyte is big data. And so here at CMC, pretty much all of the other professors besides me are muggles. And when they think of big data, they think of anything, yeah, if it's bigger than a CSV file that they can open up in Excel, then it's big data. But if you're at Facebook, so here's a link to Facebook's blog. You can read about what they consider to be big data. And in this blog, they talk about their problems that they face, and they call tens of petabytes of data a small data problem. So if you haven't heard the word petabyte before, it goes gigabyte, and then 1,000 gigabytes is a terabyte, and 1,000 terabytes is a petabyte. So 1,000,000 times bigger than these problems right here is what Facebook still considers to be a small data problem. And yeah, so Facebook's not, and Google and all these companies, they don't really disclose how much data that they create every day and how much they store. But in this post, they say that it's at least 4 petabytes per day, which is what Facebook generates. So yeah, one of the sort of biggest problems in industry, especially from a data science perspective, is this sort of clash between what people consider to be big data. And that if you're in this sort of regime where you have like 1 gigabyte and you're applying the tools that Facebook is using of like 10 petabytes of data, then you're not going to be working efficiently. And so one of the big things about this class that we'll be talking about is how to sort of understand when you're actually in like the Facebook big data regime versus when you're in the Muggle big data regime, and selecting tools that that are appropriate for whichever regime that you're working in. And so for us, big data means you're managing a cluster of computers to solve a computational problem. So something like this setting over here. And in particular, if it can be solved on a single computer, it's small data. And so the reason actually Facebook consider tens of petabytes to be small data is because they have computers that can solve that on a single computer. So it doesn't need any fancy like programming techniques to work with tens of petabytes of data when you have an appropriate computer. And these computers for 10 petabytes are expensive, but they're really not that expensive. You're maybe spending $200,000 on one of these computers, which sounds like a lot of money, but we were just looking at these salaries for engineers who work at Facebook and Google, and that's just 1 year's of salary for one person. So from a company's perspective, like Facebook or Google, spending these amounts of money for large computers so that you don't have to solve these big data problems is typically worth it. The other thing about this course, again, is it's sort of all of what I consider to be the interesting and practical and applied parts of upper division computer science that have been compressed down into just this one course. So it's everything that I think a data scientist needs to know about computer science is going into this course right here. Let's see, are there any questions so far? Okay, when we get a little bit later in class, I'll have some more interactive activities for us, but definitely feel free to at any time interrupt me with questions as I'm talking through the syllabus right here.
Oh, Professor?
Yeah, go ahead.
So is most of our work going to be done through the remote server, or will that be for the end of the course project?
Yeah, great question. So yeah, so the question's about like where's the work that you're going to be sort of working on. And throughout this whole course, you'll be working on this remote Lambda server that, that I have. And from that Lambda server, you'll be spawning new other server processes. And so roughly this first week or two, we'll be talking as review about working on a remote server. And then the next week or two after that will be how do you create all of these remote servers and work with them. Yeah, I'll be able to answer that question in more detail here in a minute, but it's a great question. Yeah, so again, feel free to interrupt me. I'm also on, I've got two monitors set up here, so I can see you all right now. And I have the chat window up on the second monitor. So if you don't feel like interrupting me, you can always write something in the chat and I'll answer or respond to it when it's a good time. Okay, so data sets that we'll work with. So a bunch of geolocated tweets, about a 4 terabyte data set, and then 2 data sets extracted from the internet called the Common Crawl and the Internet Archive, both more than 1 petabyte in size. And for these data sets here, essentially what we'll be doing is downloading them in parts, and you'll be processing them to extract information out of them. And then you'll be building your own Google search engine. So that's sort of like the culminating final project in this course, that every week we'll have a different homework assignment where you're adding a new part to this Google search engine. And by the end of the course, you'll have a fully scalable Google search engine. And the only thing that is competing you or stopping you from competing with Google, scaling to Google size, is just how much money you're willing to spend to have thousands of servers working for you. So if you have a credit card with no limit and you want to take out $1 billion loan to compete with Google, then you would be able to. Let's see, I have one of these tabs open right here. So here's an example of the search engine sort of final project, what things will look like. And so if we just start, let's do Obama. And so here's some search results down here. And then up here, if you've ever seen Google's Ngrams before, they do this for books. They don't do it for web pages at all. There's actually no, at least as far as I know, a web page that does this publicly for web pages. But the idea is we have this term Obama, and we want to know what fraction of news articles talked about Obama, mentioned the word Obama on any given year. And so we can see during Obama's presidency right here, lots of news articles talked about him, but nobody talked about him before he was president. I wonder why. And then if we were to say add Trump, then we can sort of compare how much did people talk about Obama versus how much did people talk about Trump. And maybe we'll add President Bush, and let's do Clinton as well. And so you can see over here, here's Bush, and then Obama and Trump. And then over here, when Clinton was, there we go, when Clinton was running her campaigns, you can see spikes in Clinton. And then when Bill Clinton was president, you can see him over here a little bit too. And so what I want to highlight about this is that this database right here contains a little over 200 million news articles inside of it. And you can see that we were able to run these queries, these sort of counting queries, and getting these search results in fractions of a second. And that's another sort of like big part of this course. How do we organize these really, really large data sets so that you can do these interesting queries and get your results like essentially instantaneously. Google has a policy where every web page that they create has to respond to queries within 200 milliseconds. And so Google is, I don't know, they're searching the entire internet, not just 200 million articles. And so you have to be able to search the entire internet in 200 milliseconds. And we'll talk about how they do that. You'll build a system that does exactly that. But your system's going to do more than that. It's like the entire end-to-end process of actually getting the articles from the internet, extracting the key information from the web pages, storing it in a way that's suitable for these queries to run, and then actually building a web server that can scale to thousands of users interacting with it at the same time to do these fast queries. Any questions about that so far? Yeah, so I was hoping that the IT folk would let me, so right now this is hosted on this Lambda server machine. I was hoping the IT folk would let me make this publicly accessible so that you all would have a chance to play around with it, but they decided that it's too much of a security risk, and so you'll have to wait at least a couple days until you're more familiar with the Lambda server, and so you know how to launch this system yourself before you play around with it and run what other queries you might want to run. Let's see, some other interesting ones. Coronavirus does what you'd expect, big spike over here. Turned out that about 1 out of 4 news articles during the peak of coronavirus mentioned the coronavirus. There's Brexit, that's another fun one. You can see that, yeah, by doing these sorts of queries, you can find out when important geopolitical events happened, like when did ISIS come around? There we go, mid-2014. Yeah, we'll let you play around with that a little bit later once we get that up. Okay, so technologies. What technologies will we be using to do this? So the first one is Docker containers. And this goes a little bit to the previous question about how will we actually be like launching these systems. And so Docker is the system that we'll be using in order for you to create and manage these large nodes, large clusters of computers. Docker is a tool widely used in industry for doing this. And essentially, yeah, what it does is you describe, like in just a text file, what the format of your big network architecture is, and it'll launch all of those systems for you on 1 machine or 1,000 machines, depending on how much money you want to spend. And again, in this class, we're providing all the computing resources, so you're not required to spend any money in this class. But all the techniques would scale to however much money you wanted to spend. This is one of the techniques, or one of the things that can potentially overlap a lot with other CS classes that UCS majors may have taken. So again, for the data science majors, will not have taken operating systems or networks or computer architecture or any of these similar upper division courses. But Docker containers, in order to really understand them, you have to know some of these concepts from these classes. And so we'll talk a little bit about these concepts. I think, so my experience in computer science classes is that they tend to be very theoretical about, in these courses, what they talk about, and very much not on the applied stuff. So there's a good chance that the things that we'll talk about don't overlap with courses you may have already taken, and will be more on the applied stuff, but I can't guarantee that. And then, yeah, lastly, so Docker containers widely used in industry. So this website, stackshare.io, takes you to companies that are using these technologies. So Pinterest, Spotify, Twitter, Shopify, Robinhood, Lyft, all these major companies, they're all using Docker to launch their systems and keep everything up and scalable. So it's not just all of the things that we're going to be learning in this class. It's not just things like for this class or things that are just for your assignments. Everything is going to be very widely applicable, widely used in industry. It's a very applied class this way. Yeah, so we'll spend about a month talking about these Docker containers and how they work and how you use them. But then the real focus of this class is going to be on database systems. And the database, so it stores and accesses our data efficiently. And so we'll start talking about this database, SQLite, which is used when you have an application and a database on the same server. Any of you who have Android phones, all applications that are on Android phones use SQLite to store their information on the Android phone. Yeah, so it's very common in mobile development. A lot of very small scale web pages will use SQLite as well, but typically for web pages, we'll be scaling up to, like, some people would call this a real database instead of a fake database. And so Postgres will be the main database system that we use in this class. And the main use case of Postgres is when you have like one computer that does the database storing the data, and then you have many computers, potentially hundreds or thousands, that are doing the computation on the data. And so this will be again, the focus of this class of how to use Postgres to do this. We'll also talk a little bit about this situation right here, where you have not just one database computer, but maybe a cluster of database computers that are all in the same data center. But something that we will not talk about in this class is what if you have a cluster of computers that are spread out throughout the entire world. And again, this is sort of into the Facebook big data sort of definition, in that they have to handle the case when yeah, they have users all over the world. They have 14 data centers all over the world last time I counted. And how do they coordinate all those data centers with each other? So yeah, not too much on this, mostly on these two aspects that we'll focus. Languages in this class. So Python to build our applications, and then SQL, which is the language of databases and Postgres in particular, to actually do the data manipulation. We'll talk a little bit about this phenomenon called Nosql Databases. MongoDB is the most famous of those. And I'm very opinionated about this, and I think all of those things suck, and I'll explain to you why they suck. Feel free to disagree with me, but so there's a joke in the Postgres world that people who care about their data use Postgres. People who don't care about their data use MongoDB and all these other things, because well, they actually provide no guarantees that the database is even going to store your data. Let's see. Yeah, so our search engine, I did all the examples in English, but it actually works in more than 70 languages. We'll talk about how that works. And yeah, again, Postgres widely used in industry. I'll let you explore the StackShare site yourself to see companies that are using it. So with these technologies, it's everything you need to create a fully functioning, highly scalable web business. And so one former student who's a senior thesis student last year created this Nextstorm business. And this is not a high scalable business. It doesn't need to interact with big data in any way. But this is one of the sort of things that will come out of you being able to, of this class. So yeah, in this business, I just pulled it up right here. What he's doing is essentially like a library checkout system. Claremont McKenna and a handful of other, I think he has 3 other customers right now, use this for distributing books among students. Okay, so that's a high-level overview of this course. I think this is the part that I really want everybody to pay attention to right now, though. Who should take this course? And so if you do have questions about like this section right here, please interrupt me and let me know. So again, this course is designed for data science majors. So again, CMC just approved their new data science major, and this is sort of like the CS course, the culminating CS course of the data science major. And so it's designed to meet those students' needs. And again, I'm happy to have CS majors in this course. I think you'll think it's a lot of fun. It's a lot more applied and practical and the fun things of computer science than a lot of the other computer science courses. But I also want you to know that you probably have not fully met the prerequisites for this course. So I just earlier this morning got an email from the registrar, and out of the 21 students who are registered, there are 4 students who have actually met the prerequisites for this course. And that's okay. I think as long as you're aware of the things that you don't know going into this course, you'll be fine. But you need to be aware of that and know that in some parts of the course you may have to do a little bit of extra work. And then, yeah, I've mentioned this a little bit before, but so some material in this course will duplicate material in other CS courses. And the main course that this will happen with is CS 133 Databases. So I've recommended to the Harvey Mudd and the Pomona CS departments that students not be able to take both this course and the databases course for credits. As far as I know, neither of those 2 departments have made a decision on this about whether that's allowed or not. But if you really wanted to take, say, this course right here, which would be a more theoretical version of the databases course, then you should be aware of that you may not be able to take both courses for credits. And that would be something to talk to your department about. Okay, so now let's go into detail about these prerequisites and what is the overlapping content. So discrete math, I think most people have taken this, but the real key thing that we're going to need is just some basic counting and probability. So I'm pretty confident that even people who haven't taken this yet or taking it concurrently, you'll be okay with this material. This is not too hard material. Similarly, the Foundations of Data Science is a required course, and this is one of the courses that most of UCS majors haven't taken. And the main thing that two things that you should have been exposed to in this course are some basic SQL commands already and regular expressions. It's roughly like 1 week's worth of material on each of these 2 topics. And so when we get to these 2 topics in this course, you may have roughly a week's worth of material to do in addition to the other material for the course. So if you haven't taken this course, just know that those are two concepts that we will be using. And then data structures. So there's a lot of different data structures courses offered at the Claremont colleges. And I just want to overview how CS46, which is the data structures for the data science major, differs from the data structures courses that you may have taken, so that, again, you know kind of what to expect. So everybody's covered big O notation and balanced binary search trees. And we'll be using both of those throughout this course, especially in the second half of this course. Things that 46 covers that you may not have seen before are Unix shell commands, advanced Git, this Vim text editor, and sort of what I consider small scale data of analyzing multiple terabyte data sets on Twitter. I'll have sort of review assignments about each of these topics. So if you haven't seen them before, you'll have a chance to familiarize yourself with them. But again, this is one of the things that, depending on your background, you might have to spend a little bit more time on. And then other concepts. So this is from CS40. So our intro to CS class, some Markdown, HTML, CSS. This is another spot where we see some basic SQL commands and the Flask requests BS4 Python libraries. This is all the stuff that essentially goes into the aesthetic component of this web page right here and presenting the data to the user in a pretty way. Yeah, this stuff right here, I'm thinking most people won't have any trouble with. This stuff right here, some people may have a little bit of frustration with if you haven't seen it before. Are there any questions so far? Okay. So now relation to upper division CS courses. So again, data science course for data science majors. And so its purpose is to provide an overview of like the practical CS concepts. And these are the 4 classes right here that it overlaps with to some extent. So computer systems. In this course, we're going to be talking about different storage media. So tape versus HDDs, SSDs, NVMEs, and RAM. RAID, parallel versus distributed architectures. And we'll be really emphasizing the practical aspects of this rather than the theoretical aspects of this. Operating systems. So we'll be talking about like permission systems when you have thousands of users on the same machine or thousands of users distributed out over thousands of machines. How do you make sure that those users don't conflict with each other? So that's what permissions systems do. Processes versus threads. How do you say run things in parallel in an efficient way, in a way where the processes don't overlap with each other? And then this thing of virtual machines versus containers. This is related to that Docker technology of how do you spawn all of these machines and get them to actually work for you. Again, we'll be looking at only the practical side of all of this and not the theoretical side. For networking, so after you've created all of these machines, whether they're virtual machines or actual machines like distributed out, how do you get them to talk to each other and communicate with each other? So we'll be talking about just enough networking in order to be able to do that. So private versus public networks, IP addresses, TCP ports, and these things called virtual networks. For software development, we'll be talking about version control systems. So Git, we'll be using Git throughout this course. All assignments will be based in Git. This is one of the things that when I talk to industry people and I ask them like, what do students really need to know in order to be efficient at a company or in order to work well at a company that computer science curriculums don't teach them? It's 100%, they always say students need to know Git or some version control system. So that's why all of my courses, it's very integrated into the courses. And especially this one, it's going to be, you'll find throughout the course, very, very integrated. So you'll be a Git pro by the end of this course. And then things called test-driven development or continuous integration, what the difference between a microservice and a monolithic architecture is. And there's this famous sort of type of application called a 12-factor application. It's a sort of design methodology. That's the sort of the framework that we'll be building off of. But again, so this databases course is the one that has the most overlap. It's about 50% overlap. We'll be talking about SQL, very, let's see, what I consider to be intermediate SQL in this course, but what most of you will probably consider to be absurdly advanced, mind-exploding SQL. We'll actually go into SQL a little bit more than the typical database course does. We'll talk about these, all these acronyms, ACID, MVCC, and transactions. This is how you ensure that your database actually has the correct information inside of it. And we'll spend a lot of time on this indexing techniques. And this is the key part. That's how do you make these queries efficient so they run in under 200 milliseconds, and Google will include your web page in its search rankings. Things about CS133 that we don't cover. So we won't cover what's called relational algebra. Turns out that underneath the databases inside, there's this cool algebra, kind of similar to linear algebra, that handles all the data manipulations for us. We won't talk about that. It's too theoretical for this course. We won't talk about technical implementation details, how the database actually works inside under the hood, how it, from a C programming perspective and it interacting with the operating system perspective, how all of that works. We're just going to assume that the database works and is magic. And then some big data concepts that might be taught in a pure CS big data course, but will not be taught in this course are some frameworks for distributed computation, So popular ones are Hadoop and Spark. Yeah, we'll see a little bit about like why I kind of think those are actually like dumb things that nobody ever uses, or nobody should use. So Twitter, as an example, all tweets ever sent fits in under 1 petabyte of data. And I mentioned before that 1 petabyte, according to Facebook, is a small data problem. You don't need distributed systems to solve anything related to 1 petabyte or less. And so I have a friend who works at Twitter, and I was talking to him about it. They do happen to use Hadoop, but in his opinion, it was just a total mistake. They shouldn't have spent millions of dollars building out this Hadoop cluster and getting really expensive engineers to work on it, spending lots of time developing these distributed architectures. Instead, they should have just brought one of these expensive computers and then used normal programming techniques, and everything would have ran faster and been easier to program. The vast majority of companies, basically if you're not Facebook or Google or Microsoft or Amazon, these systems just don't make sense. We won't be talking about distributed file systems, so HDFS, IPFS. We will talk about S3 a little bit. So all of these big data sets are stored on Amazon S3. It's just an easy way to store data. And we won't be talking about these geo-distributed databases. So if you have 1 million computers distributed throughout the world, how do you keep them in sync? We won't answer that question. We're going to be focused just on you have 100 computers inside of 1 data center. How do you keep them in sync? Sort of question. So with all that, are there any questions about like how this course fits into your education and what you should expect from this course?
A question.
Mm-hmm.
Is there any way that maybe like before each week you can tell us some of the topics that should maybe be revised before that week?
Yeah, it's a great question. So yeah, the question is basically each week, yeah, can you get a heads up on what are the background information that you might need to know? And the answer is yes, that's definitely going to happen. So this first week is essentially some of this background information on using these remote servers. And it's, if we look in these lab instructions down here, there'll be this section right here of, if you did not take CS46 with me, here's a couple of other tutorials that you should work through to make sure that you have this background knowledge. And so there'll be similar things throughout all of the different parts of this course that if you don't happen to have this particular background knowledge yet, go do this thing. And I'll try to help you all out that way with giving you those pointers. And if at any point there's like something that you feel like you need more background on, you can always feel free to ask me, and I'll try to help you out with that. Also, if any of you, like maybe right now you're not sure about whether this doesn't fit in with what you want out of your classes, you can feel free to either see me in office hours or have a one-on-one appointment, and we can go over in more detail about like, does it make sense for your situation, whatever that situation is, to take this course. Okay, so textbook, nothing you have to buy. Basically, big data, rapidly changing field. Every textbook that exists is already out of date, and so we're going to be using online documentation for everything. And I'll point you to the appropriate links as we go through. So grades, well, the standard grade scale right down here. Here's the overview of all of your assignments. What I call labs, essentially every week, maybe skip them some weeks. Relatively easy assignments. Hopefully everybody gets full credits, 2 points each. Then weekly homework assignments worth anywhere from 10 to 25 points, depending on the particular assignment. There's this one assignment right here, which is only for people who haven't taken CS46 with me, which is analyzing this large Twitter data set using a MapReduce style of computation. We'll talk about that next week, the details of that. But the assignment is posted up here under HW Twitter. So you could take a look at that if you wanted to. But we'll talk about that next week, what you have to do for that. Where did we go? You'll have an Open Notes midterm and an Open Notes final. And the main sort of concepts that are going to be tested in this midterm and final. Let me skip up ahead here to our schedule. So here, starting off with this Docker technology, and so Devops stands for developer operations. How do you actually like control all of these systems? This is something that's only going to be evaluated through homeworks and projects. You'll never have a test that covers this material. Instead, your first midterm is going to cover all of this sort of advanced SQL commands, which we'll be covering during this time frame right here. And your midterm is going to be after, basically, I'll give it to you this day right here in class, and you'll have a week to complete it. So for people who are looking at getting a data science job, the sort of classic questions for data science jobs always include, classic interview questions always include advanced SQL queries. And so we'll be talking about, if you can do all of this stuff, then you'll be way, way prepared, totally prepared for the sorts of questions people ask in data science SQL interviews. And then down here, this sort of second half of the course, this is what starts overlapping a little bit with the traditional data structures course. And in particular, in this indexing section, we'll talk about, let's see, so in a data structures course, one of the main things that you end up talking about is a balanced binary search tree. How do you make queries in logarithmic time using a balanced binary search tree? AVL trees, red-black trees are usually the two most popular. It doesn't matter which one you happen to have learned before. We'll be talking about this B-tree data structure, which is how do you efficiently store these data structures on disk so that you can access them efficiently that way. And in a traditional data structure, or sorry, traditional databases class, this is the only indexing technique that you would talk about. But Postgres has 7 or 8 different indexes built in, and we'll talk about the differences between all of those different data structures and when you might want to use one versus the other. And again, sort of like the culminating cool thing that we'll do is that multilingual full text search feature. We'll also talk a lot about data structures specifically for counting things. So if we go back to our web page up here, search results down here, this is the indexing part. How do you get queries that match your results? Up here, this is the counting part. How do you just know how many times something occurred in a large data set? Turns out to be more involved than you might think. And we'll be talking about something called probabilistic data structures during this. And the main one we'll talk about is called hyperlog, if you have heard of that before. The final will be normal final times, and it will be mostly still on the SQL stuff because that is the sort of most important thing to take away. But then it'll be a little bit on these parts right here as well. Are there any questions? I guess in total 250 points in the class. Are there any questions about grade stuff?
Will the final be a take home like given a week like the midterm, or will that be in the time?
Yeah, take home, you'll have a week. Should be no stress about the, no time stress or that kind of stress about the exams. One last caveat, grade-wise, is that if you want an A or an A- in the course, you have to, I don't believe CMC offers A+, so that's why it's not listed here. If your college offers an A+, then include that in this list. Then You just have to watch these 2 documentaries about Unix systems and the history of Unix, or read this, if you prefer reading instead of watching, read the history of Unix section of The Art of Unix Programming. That essentially all of the techniques that we're going to be talking about sort of are born out of the Unix history and environment, and so any educated big data person should know these things, and so that's why I'm including that. Okay, so
Wait, hello, can you hear me?
go ahead.
Yeah, do you like saying like a reflection of the watching the documentaries and stuff, or how would you know if we've seen it?
Yeah, the question is how do I know? And you just have to tell me I watched it, and that'll be it.
Okay.
I trust you all to be honest with that. Okay, so there's a little bit more things that we could talk about technology policy, collaboration policy wise, but I think it'll make sense to talk about that a little bit more after talking some more about the actual material for the course. And so I'm going to skip this for now. I will highlight that if I've tried to make this course as accessible as possible for whatever disability that people might have. If you do need any sort of other accommodation though, just let me know and I'll do my best to work with you on that. And what we're going to do is jump over to this week 0 here. And so here's our nice Dilbert joke for the week, and I'll let you read that on your own. This week, here's the basic topics that we're going to be covering, and it's okay with me if we bleed over into next week with all of these topics. There's a lot here. Basically, all of this is just how do you like interact with a remote computer efficiently and effectively. The remote, here's the stats of our remote computer that you'll be working with. So it's got 80 processors, 8 GPUs, 256 gigabytes of RAM, 2 terabyte, what's called an NVMe drive. This is a particularly fast type of hard drive that's just about as fast as normal computer memory. And then 50 terabytes, it's called a RAID array of 16 normal hard drives. So this is a computer that CMC purchased for its data science program, and it's a pretty powerful computer, but it's actually probably a lot cheaper than you might have guessed it would be. The only thing that's really expensive here is these 8 GPUs. These GPUs cost about $3,000 each. Overall, the computer system costs $35,000. So without these, everything was like a $15,000 computer, which is that's an expensive computer. It's not what you're going to purchase for your house. But when you're a company, even not a Facebook company, but any company, $15,000 is nothing compared to what they're paying, salaries and everything else. So yeah, let's see. 2014, I went to Facebook to visit some friends up there, and the average desktop computer at the time at Facebook that every developer got had 64 processors inside of it and 64 gigabytes of RAM, and that was just standard issue for everybody. So this is a big computer, but it's not really in the grand scheme that big. On your accounts, you'll have 10 gigabytes of storage and 250 gigabytes of storage in this sort of slower folder. And we'll talk about how do you manage between those. What do you put on the fast stuff? What do you put on the slow stuff? And that's sort of no technical reason why I have to limit you to these numbers right here, but I'm limiting you to these numbers so that you'll have to make these decisions about when should data be on the fast types of storage systems and when should it be on the slow storage systems. But again, we'll talk about the details of that later. So every week, I'm going to have a short section on pre-lecture work for you to do. You'll never have more than just like 5 to 10 minutes of pre-lecture work. And So for Wednesday, what I would like you to do is watch this short video right here about the Unix system. Ken Thompson, Dennis Ritchie are the two inventors of Unix. So you get to hear it from their own words, what Unix is all about. And then Wednesday we'll talk about, build on that and lecture to talk about it. And then I'd also like you to print out these three cheat sheets for Bash, Vim, and Git. We'll be using these programs every day in this course. And so by the end of the course, you'll have these cheat sheets memorized, but at the beginning, it'll help you to have them all printed out. Also have a references section, which will be like the textbook for that week that you can look at. You're not required to look at this ever, though. All the material will be covered in the lecture videos. These are just if you want to see where the information is coming from or have a written source. Are there any questions about what to do before class on Wednesday? Okay. Then every week I will also have a lab section posted, and my ideal scenario for this lab work, we would all sort of be working on this lab work together. That I'll have a Zoom session opened up, sort of like a super office hours. Everybody comes in and we all sort of work on this together. Probably we're not going to be able to find a time that works for absolutely everybody to do this. So I'll try to be as accommodating as possible. And if you come up here to the issues, in this issue right here, Lab Times Survey, there's a link to this right here where you can fill out some times that would be work well for you to have these lab sessions. And I'll try to pick times that work sort of generally as well as possible. But those sessions are not required. It's sort of a totally optional thing for you to attend if you'd like to. If you do attend, let's see. So for all of these labs, the due date is going to be on the Sunday after the week. So for the lab this week, it'll be due January 31st, this coming Sunday at midnight. If you do attend the lab, then you get a 2-day extension, 48-hour extension until Tuesday at midnight. If for whatever reason you're not able to attend the lab, but you sort of create your own lab environment with other students from this class or really with anybody and work together on the lab, then you also get that 48-hour extension. So I'm trying to encourage you all to work together on these assignments. Cover the details of the collaboration policy on Wednesday, but basically, as long as you're collaborating in a way that you feel like you're learning, that's encouraged and allowed, as much collaboration as possible. The weekly homework assignments will also follow the same policies of due dates of due on Sunday, but if you work together with somebody else or come join the lab, you get the 48-hour extension. Are there any questions about that policy? Okay. Then the lab is also going to be divided into a sort of pre-lab section and then the actual lab section. Most of the time, the pre-lab work is going to be, again, super light, probably not even existent. But this time, I want you to spend about an hour working with this program called Vim Tutor before the lab. So before whenever you actually get started on doing this stuff down here. And I want to spend a second now to talk about Vim Tutor and Vim and what this is. So I'm going to switch my screen right now over to away from Firefox. And what I'm going to do is I'm going to connect to the Lambda server machine. So you all should have received an email instructions about how to connect to the Lambda server on a Windows or Mac machine. Oops.
Would you mind making the font in the terminal just a little bit bigger?
Yes, sure. Let me. we go.
Thank you.
Can everybody see this? We will connect to the Lambda server. And the first time that you connect, you'll get a message asking you to change your password from the password I provide you. One of the things that is potentially confusing is that when you're doing all of these password changes on a through a terminal system, you're not like you'll be typing things on the keyboard, but nothing will appear on the screen. That is expected and normal behavior. Turns out that's the only way to make password entry secure. If you were like printing stars or something on a terminal, turns out that that's not a secure thing to do. So that's why it doesn't print anything. So make sure that you can log in to the Lambda server. And then in order to run this vim tutor command, you just type vim-tutor and hit enter. And it will open up the Vim program and walk you through how to use it. So Vim is a text editor. It's a very special type of text editor though. And one of the things that's special about it, the first thing that's special about it is that you can use it on remote servers. So if you've used, say, VS Code before, or PyCharm, or any of these more traditional editors, IDEs, they're really designed to work only on the system that you're actually currently using. VS Code does have an ability to work on a remote server through a what I'll call a single hop, a single SSH session. And so for the first week or two of this course, you could technically use VS Code to accomplish things. But as we go through this course, you'll be working not only on a single session that's a remote computer, but you'll be bouncing through like potentially 5 to 10 different computers in order to get things to work. And VS Code will not work for that. You will have to use Vim. So it will be tempting for you to not want to use Vim if you haven't used it before, because it is a difficult program to learn, but you will not be able to complete this course if you don't master Vim. So very important that you do actually do this Vim tutor command. So that's the first thing that's unique about Vim. The second thing that's unique about Vim is that it's what is called a modal text editor. And you'll see exactly what that means through this tutorial. But essentially what it means is that when you type characters, they don't actually appear. All characters are actually commands that tell the Vim program to do something. And that's what makes Vim very confusing at first, but it also makes it sort of extremely powerful once you learn what those commands and what that Vim language is. So the first command that you need to know, the only command that you need to remember right now is how do you actually quit Vim? There's a big joke, ongoing joke on the internet about somebody types in Vim on their terminal and they're stuck in Vim forever. And because it's not obvious how you quit. And so there's 3 keys you need to remember to press. And that's first the escape key, then the colon key, and then Q. So you're not going to be able to see as I type this on the keyboard. It does actually print out in the bottom left down here, but escape colon Q is the way to quit, and you hit enter, and then it will take you back to your terminal session. So go back to Vim Tutor and just read through this, and also important when it asks you to actually do something, actually do it. Don't just read it and think about it. You actually have to do it in order to start getting your muscle memory for how to use these Vim commands. So in this course, all of your assignments, all programming, all text editing of any form, you're required to use Vim to do it. That's our first technology/collaboration policy. And that if you use any editor other than Vim, then that will be treated as an academic integrity violation. So by submitting any assignment, you are implicitly telling me that you used Vim to complete the assignment. So even though for some assignments, it would be technically possible to use something like VS Code, if you do use VS Code, then academic integrity violation. You have to use Vim in this course. And again, throughout the course, we'll see lots of examples about why it's actually good to use Vim. If anyone here happens to already be an Emacs user, then I feel sorry for you, but you are allowed to use that as well. I will not force you to use Vim. You can use Emacs if you choose. But if you haven't picked one between Vim and Emacs, then go ahead and use Vim. Are there any questions about that? Okay. The last thing that I want to point out, so we already saw this issues tab a little bit. This is where we'll be doing all of the communication throughout the course. So whenever I have an announcement in class, I'll be posting it here. Whenever you have a question about why is my code or commands not doing what you think they should be doing, this is the place where you can post your question and I will answer them for you. In order for you to get updates about the course, what you'll want to do is you'll want to be watching the course. And so after you log into GitHub, you just come up here and press this button right here, and you'll be watching the course. And then every time I post a new update, you will get an email about what that update is. Let's see, we have a few more minutes left in class, but rather than talking about more stuff, I want you all to just try to log into the Lambda server and make sure that that process is working for you all so that you can get started on especially this Vim tutor assignment, learning to use Vim. And if for whatever reason you are having troubles logging into the Lambda server, I'll be available right now to do admin troubleshooting to help you out. Or if you have other questions about anything else about the course, I'll be available to answer those as well. But again, yeah, so for Wednesday, the things to do, this pre-lecture work, watching this video right here, printing out these cheat sheets, having them available for you for Wednesday, and then get started with this Vim tutor command. Also, as soon as you're able to, please fill out this lab time survey so we can have a more scheduled time for these labs for those who would like to be able to do those. I'm going to stop sharing my screen now. And I guess that's sort of the official end of the things that we need to talk about for this intro day to big data. But yeah, I'll be here to help troubleshoot people who are having problems logging into the Lambda server, or if anybody else has questions about the course. And I will stop recording